Okay, we are going to see cogging and crawling in cage motors. Cogging. Cogging is a phenomenon of magnetic locking between stator and the rotor teeth. That is also called teeth locking. Even after applying full voltage to the stator winding, the rotor of a three-phase induction motor fails to start. This condition arises when the number of stator and rotor slots are either equal or have an integral ratio. The number of stator slots equal to or integral multiple of the rotor slots, a strong alignment of force are produced between stator and the rotor. Like, see, if our stator is having four number of magnetic poles, stator, north pole, south pole, north pole, south pole. Our rotor is also having equal number of rotor poles. Like this alignment comes like this. Under this north pole, one south pole is coming. Under this south pole, north pole of rotor is coming. Here, one magnetic strong force of magnetic interlocking will happen. So our rotor fails to start. Similarly, if our stator is having four number of stator slots and rotor having two number of slots, that is the integral multiple. Here north pole and here south pole, and here north pole and here is south pole, north pole and here is south pole. Then here strong magnetic force will happen and the rotor fails to start. That is the two conditions. The number of stator pole slots equal to integral multiple of rotor slots. A strong alignment of force are produced between stator and the rotor. As the result of these forces, an alignment torque greater than the accelerating torque with consequent failure of the motor to start. That is the cogging. Motor fails to start. Thus, a locking is created between stator and the rotor teeth. This condition is cogging or magnetic locking. When the stator and the rotor teeth face each other, the reluctance of the magnetic path is minimum because the reluctance between the magnetic path is minimum. That faces each other. Under this minimum reluctance path condition, the magnetic locking takes place between stator and the rotor teeth. In order to reduce or eliminate the process of cogging, the method is the number of stator slots is never made equal to rotor or has an integral ratio. Number of slots. In the slots, we are placing the winding. That winding produces the magnetic poles. It can also be reduced by using a skewed rotor. That is, the rotor is having slots like that, like this. Not a straight slots, skewed slots we are using. Cogging and crawling are less eminent in wound rotor motor because they are having high starting torque. Slip ring induction motor or wound rotor motor is having high starting torque. Next, that is the cogging. That will always in most of the question paper, the cogging is asked as writing short note. Similarly, crawling. Crawling, that is also a phenomenon in induction motor. It has observed that squirrel cage type induction motor has a tendency to run at very low speed compared to its synchronous speed. That means synchronous speed is ns. Always motor speed n, that will be less than ns. Okay, so in the condition of crawling, the speed of the rotor of the induction motor is very much less than synchronous speed. The resultant speed is nearly 1/7 of its synchronous speed. Why this crawling happens? This is due to the fact that harmonic fluxes produced in the gap of the stator winding of the odd harmonics. That is, the odd harmonics are third harmonics, fifth, seventh, etc. These harmonics create additional torque fields in addition to the synchronous torque. The torque produced by these harmonics rotates in forward or backward direction at the speeds ns by 3, ns by 5, that is synchronous speed. 1 by 3rd of synchronous speed, 1 by 5th of synchronous speed, and 1 by 7th of synchronous speed. Here we are considering 5th and 7th harmonics, and rest are neglected. Higher harmonic components are neglected. The torque produced by the 5th harmonic rotates in backward direction. The torque produced by 5th harmonic was as a braking action is small in quantity, so it can be neglected. Torque produced by the 5th harmonics, which was as a braking action in small in quantity. So this can be neglected. Now see, what about 7th harmonics? 7th harmonics produces a forward rotating torque at synchronous speed ns by 7, 1 by 7th of synchronous speed. Hence, the net forward torque is equal to sum of the torque produced by the 7th harmonic and fundamental torque. Okay, torque produced by the fundamental component. That is the frequency, supply frequency. The torque produced by the 7th harmonic reaches its maximum positive value just below 1 by 7 of ns. And this point, the slip is high. We know our rotor speed is always just less than the synchronous speed. So the torque produced by the 7th harmonic reaches maximum positive value just below 1 by 7 of ns speed. At this stage, motor does not reach up to its normal speed and continue to rotate at a speed which is much lower than its normal speed. This causes crawling of the motor at just below 1 by 7 of synchronous speed, and it creates the rack. The other speed at which motor crawls is 1 by 13th of synchronous speed. So usually in crawling, motor runs at a speed 1 by 7th of synchronous speed. This is due to the harmonic component. That is all about cogging and crawling. Always these are asked us writing short notes. Thank you.